So you want to move your TV somewhere else, and you go to your favorite hardware store or big box store, and you get maybe 100 feet of cable like this, and you look on the packaging or maybe online, and it says the impedance of the cable is 75 ohms. So you go, okay, if it's 75 ohms, let's test it before we actually use it to make sure it's okay. So what you do is you decide to measure the outer connector or shield and the inner conductor of the cable with your favorite ohm meter, and it shows there's an infinite number of ohms. Well, I guess that sort of makes sense because the two wires are supposed to be insulated. Well, maybe it's 75 ohms if we measure from the center conductor on one end to the center conductor on the other end. And what do we get? We get somewhere around 1 to 1.5 ohms. So that's not 75 ohms either. Well, were you ripped off? The answer is no, we're just measuring it wrong. And to see what's happening, what we need to do is look at it in a little bit more detail, and we're going to use a signal generator to generate a rectangular shaped pulse to investigate what's going on. So I'm using this little cheapo signal generator here, and to make my life easier, I've actually got it set up using the remote control panel on a PC, and I can do things like change the duty cycle just by clicking on the PC and having a much bigger display that's, well, easier to access with a mouse than reaching across the electrical bench. So to see what's going on, we're going to have our signal generator, which we'll draw like this, and it's going to output the pulse, a very narrow pulse like that, and it's going to go through a resistor, and then we're going to attach our wire, our cable, to the resistor like that, and the outer shield of the cable, the return wire if you want, will get connected to the ground of the signal generator and the ground of everything else to try and minimize noise. And to see what's going on, we're going to use our dual trace oscilloscope over here, and we're going to attach one of the leads from the scope up here so we can see the pulse, and we're going to attach the other lead of the scope over here so we can see what's happening right on the other end of this resistor, right where the signal goes into the cable. And we'll display it something like this. On top we will see our pulse, and we'll expand it so much that this narrow pulse is now stretched out way over there, so we can just look at the very leading edge, and the output, if you want, the interesting part about what's going on in the wire, will show below like this, where it'll maybe do something interesting. Here's the actual setup. The signal from the signal generator, the pulse, comes down this red wire, and it actually goes into a bit of a resistor network. We won't worry about that, but the whole thing is designed to essentially look like a single resistor, just like in the drawing. We measure the pulse using this oscilloscope probe over here, the pulse coming right out of the signal generator, so there's no funny business. And we also measure the pulse as it is seen at the end of the wire, and we're going to use these two leads over here to connect to the wire. Way over there you can see the graph on the oscilloscope. Over here is the signal from the signal generator, and here is the signal which would be attached to the cable but isn't so far. So now we'll attach our leads to the cable. And to make our lives a bit easier, we'll use this little adapter here to do the attachment. We'll attach our ground to the outer shield, the outer wire of the cable, and we'll attach the yellow lead, which has the signal from the signal generator, to the center conductor of the cable. Did you see what happens? The signal dropped from being at full height to being at a much lower height, in fact about half the height, for about, if we look at the sweep rate, 250 nanoseconds, and then the signal goes up and is, well, the same amplitude that it was before. What could be happening? Well, to see what's happening, let's attach a second 100 feet of cable, or about 30 meters of cable for you in metric countries. Oh, did you see that? The edge now moved over another 250 nanoseconds. Without any cables, we had an identical step as the signal we're putting in, an identical pulse. With one cable, the pulse went up to half the height and then stopped, and then 250 nanoseconds later it went up to full height. And now with 200 feet of cable, it takes a full 500 nanoseconds before we go from half height to full height. Well, how does that pulse know how long the cable is? Because there's clearly something to do with the length. So the question is, what on earth is going on here? And well, we can get a better idea if I adjust the settings on the scope so we can see both ends of the pulse we're transmitting. Well, if we look here, once again, our pulses start at the same time. There's a certain delay, and then the signal at the input to our cable goes up to full height. And then after a certain amount of time, the signal at the input to the cable drops just at the same time that the original signal drops, but there continues to be a half height voltage, a half voltage on the output that lingers on for another 250 nanoseconds. Well, there's our hint right there. And what we'll do is we'll actually maybe start reducing the size of our pulse to see what's actually happening. So we're making the pulse narrower and narrower and narrower. And if we make it very narrow, like that, we begin to get an idea. If we look at what's happening now, we have only a half height pulse, and then around 250 nanoseconds later, we get a somewhat distorted half height pulse again. Well, this half height pulse is the pulse we're seeing at the junction of the resistor and the input to the cable. And what I didn't tell you was that resistor that I've set up is in fact 75 ohms. The fact that this is half height tells us that that resistor for this short period of time is in fact seeing 75 ohms at the input of the cable. And then miraculously, sometime later on, 250 nanoseconds later, we see another pulse. Well, that pulse is in fact the reflection from the other end of the wire. So this pulse is in fact shooting down the wire at almost the speed of light, in fact 80% of the speed of light, and when it gets to the end it gets reflected back. And here is the return pulse. It's a bit like radar. Now, if you don't believe me, let's look at what happens if I short the end of the wire, the other end of the wire. What do you think is going to happen to that reflected pulse? Well, here we go. Well, it looks like it's disappeared, but that's a bit deceptive because of the oscilloscope trace. I'm going to move everything up by a certain amount, and now watch what happens when I short the end of the wire. That pulse suddenly goes from sticking up half a height to sticking downwards half a height. In other words, it now has a negative voltage. So why would that be? Why does the pulse go from being a positive half-height pulse to a negative half-height pulse when I short the end of the wire? So why does our pulse end up being reflected? Well, here's our wire, and we'll actually call it a transmission line because that's the correct terminology. And we send our pulse racing down the wire at the speed of light, and usually for a cable like this, the speed that it goes is about 0.8 times the speed of light in a vacuum. And that pulse consists of a voltage and a current. So we have a voltage and a current racing down to the end of the wire. And what happens at the end of the wire? Well, when the wire is open like this, the voltage at the end of the wire is really free to be whatever it wants to be. However, with nothing connected here, there is no place for that current to go. And it turns out mathematically there is only one solution that can happen, and that is if we have a current going in this direction and it can go nowhere, it means there has to be an equal and opposite current going in the other direction. And so we have an equal and opposite current going in the other direction, in other words, back towards us. And we also have that same original voltage, so in the end we have another pulse, this time racing along back, and that is our reflection. And what we see on our scope is the pulse we sent, and then about 250 nanoseconds later, a somewhat distorted pulse that is the reflection. And if you're wondering why it's distorted, well, it's distorted because this is a rather high frequency pulse, and when we lose some of the high frequency content, it tends to round it and mess it up a bit. All right, you say, but that doesn't tell us why the pulse gets inverted when we short the end. Well, we can do that too. Here's our transmission line again. We have a pulse, a nice perfectly shaped pulse shooting down it, a certain current and a certain voltage. Only this time we've shorted the end of our wire. What happens when our pulse gets here? Well, the first thing is any current can flow because it's shorted, so no big deal there. But the voltage across here must equal 0. So what happens? We have a current flowing in this direction. We have a voltage that equals 0, but we also have our pulse coming down here, and it's not equal to 0. Well, once again, mathematically, there is only one solution that will satisfy that, and that is if we have another pulse with a negative voltage that ends up going in the other direction, such that at this short over here, these two voltages add together to be 0. So we have our minus voltage and we have our current over there, and that creates our reflecting pulse coming back over here. So over here we see our original pulse, and then we see our somewhat distorted negative pulse coming back from that short. Now, you might say, well, if that's an open circuit and we get a positive reflection, and this is a short circuit and we get a negative reflection, what happens if we put something in between? Well, let's do that. So that something in between is going to be this 75 ohm resistor. Gee, I wonder if it's just a coincidence that I picked 75 ohms, and I'm going to hold it at the end nicely like that. And, well, let's take a look at what happens to our pulses on the scope. And there you go. Our pulse completely disappears. So, what does that say? Well, it says that if we add a 75 ohm resistor to the end of our transmission line, none of the signal gets reflected back. And we could say it looks like we had an infinitely long transmission line. And that's in fact where the characteristic impedance of 75 ohms in the spec comes from. If we had an infinitely long transmission line going from here to the end of space and time, and we attached a ohm meter to the end of our cable, we would see 75 ohms. So maybe what we should do now is make our pulse nice and long again and get a better sense of what's going on. So what's happening here is, for 250 nanoseconds, the time it would take for the signal to get to the end of the wire and come back, we don't see any reflections. And so we simply see the 75 ohm characteristic impedance, which cuts the voltage going into the wire by half. At the 250 nanosecond point, well, we start getting the reflection back. Its voltage adds to the original voltage, and now we get the full voltage we're applying to the wire. And of course, to us that looks like an open circuit, because normally this is so short we don't even notice it. And then similarly, after the pulse stops, we still have 250 nanoseconds of reflected power coming back. So that's all good and well, but why is it important that we pay close attention to the impedance of transmission lines? Well, as we saw, if the impedance of the transmission line is different from the impedance of the load, a certain amount of signal gets reflected back. And if you're out in the country and have a weak signal coming into your TV antenna, well, that means you're going to lose a certain amount of that signal. But there's another interesting thing, and that is, what happens if we have two TV sets and we say, you know what, maybe what we should do is just take a couple of coax cables and we'll connect the ends together like this, and we will attach them to our incoming wire by connecting it together as well. What do you think is going to happen? Well, if you consider that each one of those wires is hopefully properly terminated and should be 75 ohms, well, what that means is the incoming signal is going to see two 75 ohm resistors in parallel, which will produce something like 37 ohms of effective resistance. And what do we know? It should reflect. Let's quickly try that. I've hooked them together here. I've actually prepared these wires, so I've put a 75 ohm resistor at the other end to simulate a TV set. Let's see if we get a reflection. So did you see it? We went from a nice big positive reflection before things were attached to a slight negative reflection when we attach the joined together cables, and the reflection is negative because the impedance is less than 75 ohms. And what that means is a certain amount of our signal that we're sending is in fact being reflected back to the source, which might be our antenna, which would really be a waste of good signal. And that, my friends, is why when you're attaching two TVs to an antenna, you use a splitter like this. What it does is it makes sure the antenna going into here sees 75 ohms in spite of the fact that two 75 ohm cables are attached to it. And there's generally some sort of resistive inductive capacitor network in here to compensate for that. Well, that brings this video to an end. I hope it gave you a sense of what reflections are in cables. And if you think of radar, well, yeah, it's essentially radar in a cable. This is typically called time domain reflectometry. I don't know who came up with that term, but that's what we use when we're talking about radar and cables. If you have an expensive cable like an underground transmission line, you can use techniques like this to figure out how far away the break is, because the break will be a change in impedance and you'll get a reflection back. And if we know the speed of light, which we do, well, it's easy to calculate where that break is. And I didn't mention it, but it's worth noting that the speed of light is roughly 1 foot per nanosecond. So that's your calculation right there. And the reason we were seeing a 250 nanosecond round trip delay for 100 feet was because the speed of light is slowed down when it's in a cable, and about 80% of the speed of light, 80% results in the 200 nanosecond round trip time being scaled up to about 250 nanoseconds. Still very quick. Now, if you're wondering how other reflections occur, mirrors, reflections from glass, and so forth, well, we'll talk about that in some future video. I hope you enjoyed this video. See you next time.